Before we discuss the t-test, let's take a moment to review the central limit theorem. Recall that we often find ourselves with a sample of data. And for that same sample, we can plot it using a histogram and then calculate some descriptive statistics, such as the mean and the standard deviation. Now here, you can see that my sample does not appear to be normally distributed. Second, I've called it sample 1 because we will consider it in relation to sample 2 in a few moments. Recall that the central limit theorem tells us three things. First, if we took a whole bunch of samples and plotted their means, then this sampling distribution would be normally distributed. Now this is even though the sample itself appears not to be normally distributed. The sampling distribution is the theoretical distribution of the sample means, not the distribution of the data we actually have. They're different. Second, we can use the descriptive statistics from our sample to estimate the population parameters of the sampling distribution. Specifically, our best estimate of the mean of the sampling distribution is our sample mean. This seems reasonable. And our best estimate of the so-called standard error of the sampling distribution is the standard deviation of our sample divided by the square root of the size of our sample. This part may or may not seem reasonable to you. You're going to have to take my word for it. You can be certain that I did not write out a mathematical proof of this either, so I'm taking someone else's word for it as well. The point is, once we parameterized our sampling distribution, we can calculate some confidence intervals around the population mean. That is, we can say our little sample provides our best guess of the true underlying population mean, but then we can estimate our degree of uncertainty based on the size and variability of our little sample. So, for example, we could say that we are 95% certain that the true population mean is within the shaded region. Or we could decide to state our estimate with 99% certainty, but of course that would lead to a much wider shaded region. What happens if we want to compare two samples? This happens a lot in gap analysis. We want to know if one sales promotion campaign, the new expensive one, is really better than what we are doing now. Or we want to know if the incidence of, say, brain cancer in one sample, those with smart meters or living closer to wind turbines or whatever, is really higher than the incidence of brain cancer in a different sample that does not live near the offending technology. As before, we can visualize our two samples using a histogram. In this case, my samples are blue and red. Although they seem to be different, there is enough overlap that it's hard to come out and say with certainty that red is greater than blue. At the same time, we shouldn't say it's too close to call, because it seems that by and large, red is in fact somehow greater than blue. Now, if we can't say anything certain, but we still need to say something, we should quantify our uncertainty and state a probabilistic conclusion. One way to do all this is to draw on the central limit theorem and this idea of confidence intervals. We know that each sample permits us to estimate the mean of the sampling distribution and to put confidence intervals around that estimate. If, as is the case here, the confidence intervals do not overlap, we might feel that it's reasonable to conclude that the blue sample, sample 1, and the red sample, sample 2, have different sampling distributions. When we translate this into business terminology, we say the two samples are significantly different, or statistically different, or maybe just different. We need to take two things into account when determining whether two samples come from different populations. The first is obviously the difference between the means of the two samples. Anytime we take two samples, even from the exact same population, we should expect to get some sampling error, which means the means from the two samples will be different. But at what point does a difference cease to be just sampling error and start to be evidence of a significant difference between the samples? Let's define the difference between the two samples as the Greek letter delta and consider what happens when delta gets larger. Hopefully you can see that as the difference between the sample means increases, the likelihood that the two samples are from the same population decreases. Second, we have to take into account variability, typically expressed in terms of the standard deviation or the variance of the samples. If our underlying data is highly variable, our confidence intervals for the two sampling distributions will be wider, meaning that we can be less certain that the two samples are truly different. We capture these two dimensions with a ratio called the t-statistic, delta over variability. The exact measure of variability depends on a couple things, not least whether the two samples have the same variance. Now, if we expect two samples to be from different populations, we might then also expect them to have different standard deviations. Unfortunately, that complicates the math a little bit. The good news is that we never calculate the t-statistic by hand, so you really don't care that much about the math or have to know different formulas for when we assume equal or unequal variance. That's why we have computers. But it's worthwhile to understand the basic operation of a t-test. We start, as usual, with two samples and calculate the difference between the sample means, and then we also compute a combined measure of standard error for the two samples. The ratio of these gives us the t-statistic for the two samples. Now, it turns out that this t-statistic is distributed according to the t-distribution. Moreover, if we assume that the two samples are from the same population, we can say something pretty strong about this t-distribution. We can say that it has a population mean of 0. Thus, if we took a whole bunch of pairs of samples from the same population and subtracted the sample means in each pair, we should naturally expect the average difference, or the average delta, to be 0. So we can use this plus the observed standard error, just as we did before, to construct confidence intervals around this population expected mean of 0. Now, one of two things is going to happen when we compare this to our observed t-statistic. Either the observed t-statistic is going to fall within the confidence interval, which means the difference between our two sample means falls within what we might expect as sampling error. And in that case, we can't really conclude that the two samples are different. Or, in contrast, the t-statistic is going to fall outside the confidence interval. And we see this as a very unlikely outcome given our assumption of 0 difference between the sample means. This is precisely what a statistics package gives us, except the idea of a fixed confidence interval and critical t-values is a bit old-fashioned. To illustrate, consider the output from a t-test in Excel. Now it seems like there's a lot going on here, but it is actually pretty simple now that we have some idea of what is going on under the hood. At the top of the output table, we have the descriptive statistics from the two samples. Now, Excel uses this to calculate the t-statistic, which in this case is negative 63.9. Now, we don't really care about the t-statistic. We are more interested in the probability of getting a t-statistic that large, given the assumptions that the two samples are from the same population. That is, we find it easier to think in terms of probability and likelihood than t-values. Excel considers our observed statistic against a theoretical t-distribution that corresponds to this no difference between samples assumption. It then calculates the probability or p-value of getting a t-statistic that big or that small. However, keep in mind that we entered this whole comparison simply asking whether the two samples were different, not whether one sample mean was greater than the other. When you have really strong prior beliefs about the relative size of the sample means, you may say that one is bigger than the other and then conduct a one-sided test to test that statement. But here we're conducting a two-sided test, meaning that we are looking for the probability that the two means are different. The reason this is called a two-sided test is because we must recognize that the sign of our t-statistic, which just happens to be negative in this case, is somewhat arbitrary. If we had subtracted the mean of sample 2 from the mean of sample 1, we would have got a negative delta like we did here. But if we had reversed it, we would have got a positive delta and thus a positive t-statistic of 63.9. So since our t-statistic could have been either positive or negative depending on how we organized our data, we have to consider the extreme tails on both sides of the t-distribution. That's why it's called a two-tailed test. What we're left to is similar to a confidence interval. It says that the probability of getting a t-statistic with an absolute value greater than 63.9 is basically zero, which is the two-tailed result reported by Excel. Now sometimes in Excel you see a number with a negative exponent like 3.5 e to the negative 12, which means a decimal point with 12 zeros to the right of it, followed by a 3 and then a 5. Any number that's more than a few places to the right of a decimal point is effectively a zero, so extremely unlikely. So what we conclude in this case is that since the probability of the two samples being from the same population is effectively zero, we conclude they're different or that a gap exists. Let's switch gears here and talk about doing a histogram and then a t-test in Microsoft Excel. To start with the histogram, what I have done here is I've extended the frequency table I did when we were doing histograms and split it into a separate column for male bank employees and female bank employees. What I want to do is get sort of a visual image of whether the distribution of pay varies by gender, which is really the first step in knowing whether we have a gender discrimination problem in our bank. Once I've got that frequency table created, and I'll leave that as an exercise for you now that you know how to do it, I get the following histogram, which really has two series on it, male and female employees. What you can see if you look over at the far right is that we have a lot of employees, or at least a couple of employees, who make a lot of money and who just happen to be male. Now, we might call these outliers, or we might call them critically important data points. The answer, which one it is, outlier or critically important, depends on the business context. In this case, you could probably argue that these high-paid employees are paid on a different basis than the rest of the employees in the bank. For example, managerial employees and the top leadership team may negotiate their salary, whereas everyone else, the worker bees in the firm, are paid according to some written policy. Now it's really the written policy we're interested in. Therefore, we might be justified in censoring or removing any salary over, say, $80,000 from the data set. When we get to the other half of the data set, on the left-hand side, the visual gap analysis is not particularly compelling. It's very hard to eyeball this, which is precisely why we use a formal tool like a t-test. I'm going to start this demo with a really simple t-test and then move on to something which is a little bit more realistic. The important thing to notice about my data here is that it's in two columns. It's sample 1 on the left and then sample 1 on the right. And the actual rows, whatever's in row 2 or row 3, doesn't really matter. They're completely independent samples, but they're lined up in column A and column B. So what I'm going to do is I'm going to click on data and then data analysis. And that's going to bring up the data analysis tool pack that is an add-in to Excel. Now, if it doesn't show up, you should Google find data analysis tool pack in Excel, and there's literally a million videos on how to find it. The next thing I look at is I see there's actually 3 different types of t-tests. Now, what I said a minute ago is that we have 2 samples. And previously, we talked about whether or not we'd have equal variances or unequal variance. Since at this point we don't know what the variances are in these 2 samples, the safest choice is to assume unequal variances. So I click OK, and I get this dialog. Very straightforward. What's sample 1? What's sample 2? They didn't call them samples, but they probably should have. So sample 1 is whatever's in A, and sample 2 is whatever is in B. Now notice that I select the labels. This is going to make the output a lot easier to read, but I also have to tell Excel that I took the labels. Don't worry about the alpha or anything like that, because you'll see we're more interested in p-values. The output range is where I want to put the t-test. I'm just going to stick it on the same page, but there's one thing you have to be very careful about in Excel, is when I selected output range, you'll see that the focus, the cursor, went back up here, which really tempts you to clobber your first range. What you have to do is, after you select output range, is click here and then find a place to put your output. I'm just going to put it anywhere. When I'm done, I hit OK, and I get a tableau or an output table, which I can resize and take a look at. Now, we saw this previously. It tells me that I have 2 samples, sample 1 and sample 2. That's the advantage of selecting the labels. It tells me that the variances are close, but not exactly the same. There's some rules of thumb for determining when variances are the same or different. I prefer to do this in something like SAS, which tells you explicitly which assumption to use. But what I'm really interested in is this p-value. This is the probability that sample 1 and sample 2 have the same population sampling distribution. Or put it more simply, this is the probability that those 2 are the same. They come from the same population. Now, that's an absurdly small number, and if I resize it, you'll see that it rounds to 0. So basically, there's almost no chance that sample 1 and sample 2 come from the same population. For this t-test, we're going to go back to the bank data. And the bank data isn't nicely laid out into two columns like my previous example. In fact, it's more characteristic of data you'd get from a relational database or a corporate information system. We have gender here as a column, and we have the salary for each employee as a column. So in a sense, this data is stacked. That is, the male salary data and the female data are stacked on top of each other or interleaved. What I want to do is unstack them, or what you might call pivot the data. And not surprisingly, one of the best ways to pivot the data without sorting or doing a lot of manual work in Excel is to use a pivot table. So I'm just going to put my cursor anywhere in my data and go Insert Pivot Table. And it automatically selects the correct data and gives me this little pivot table. So what I want is, the bottom line is I want salary as my value. And right now it's giving me the sum of salaries in the organization. And then what I want along the left-hand side in the rows are my employees. I'm going to use the employee ID here. In this way, I get 200, all 200 and some employees. I just get the person and the sum of their salary, which in this case is just their salary because there's only one piece of data per employee. Now the trick here is to take the gender and put it across the top. And if you see what happens here, it creates a female column and a male column. That is, it takes the value of the gender column and puts it across as row values. That's what a pivot table does. Now before I use this, I just want to get rid of the grand totals and all that. So I look at pivot table options and I search around until I see totals and filters, and I see my grand totals, and I can hit OK. So now what I have is pivoted data. I have two columns, one for female employees, one for male employees, and they both contain the salary data, which is precisely how I need the data in Excel in order to do a t-test. Now that we have our data in the right format for Microsoft Excel, creating the t-test is as simple as it was before. So we go Data, bring up the Data Analysis Tool Pack. Again, we have two completely independent samples assuming unequal variances. And again, we select our ranges. In this case, I select females first, make sure I get them all. And then I select my males, make sure I get them all, including the label. Click the label, click the output range. Be extremely careful to put the focus where it belongs. Select a spot, and then I get my tableau. Now what this is telling me, that females on average are making $37,200 a year. Males on average are making $45,000 a year. If you want to, we could calculate the difference, the practical difference in terms of dollars, as just about $8,300 difference. Is that real, or is it sampling error? Well, if we come down to the two-tailed test, we see that the probability that females and males, that these samples are coming from the same population, is approximately 0.